Assalamualaikum and hello to everyone. Today I will sharing about the effect of bismuth addition on radiation shielding and elastic properties of mixed ionic electronic glass system. So my name is Muhammad Siddiq Fadhil bin Sutrisno with my co-authors Ashmi Bihaya and also Rosdiana binti Hisham for this international symposium on radiation physics. So this is the flow. First, we will go to the introduction, and then we go to the objective, methodology, and last will be the result. For introduction, for the glass system, so they have two common characteristics. First is no long range order and no periodic arrangement. And specifically for oxide glass, they have network modifier, network former, and intermediate, and we have the structural glass with those two unit. First is the bridging oxygen unit, and second will be the non-bridging oxygen unit. Okay, you can see from here whenever we add the modifier, and then it will convert the TO4 bridging oxygen to TaO3, the non-bridging oxygen. Usually, whenever we add the modifier, then non-bridging oxygen will be increased, and the formation of non-bridging oxygen will increase the properties of those glasses. In this case, you can see whenever we increase the bismuth, then it will increase the conductivity. Okay, usually until 15 mole percent bismuth. But we observe the nonlinear result here with the minimum here actually. So it is due to the mixed ionic electronic effect that is observed usually in conductivity and elastic properties. So now we want to see whether this mixed ionic electron effect will have also in the addition shielding and also elastic properties of our glass sample. So this is our methodology. First, the chemical powder will be weighed and also will be grinded, and then it will be fabricated by using melt quenching method. Okay, the details is here, and then for the structural measurement, we will use FTIR, and then we simulate the glass sample in simulation on PSPSD for the radiation shielding properties, and the calculation on bond compression model for elastic properties. This is the flow result and discussion. We go to the density and then the radiation shielding properties. Okay, and last will be the elastic properties. So for the density, you can see from here actually whenever we increase the glass sample, we can see the drop at 11 mole percent. It is due to the mixed ion electron effect. So addition of bismuth will at some time will induce the blocking effect and then lead to low formation of NBO, which decrease the density of the glass. So whenever the density of the glass decrease, then it will also affect the radiation shielding properties of our glass sample. This is the linear attenuation coefficient of our glass sample. We have three region whenever with increase of photon energy that we observe due to the photoelectric absorption, complex scattering, and pair production. For the increasing bismuth, we can see that the LSC, which indicated the total probability of radiation contact with a medium, is increased but have a drop at 11%. So it is due to the drop in density of the glass. For the photon energy dependency, so we can see the LSC is decreased at first at photoelectric effect region. So it is due to the transmission of photon energy. And then Compton scattering, we can see that it is actually constant and also at the low value. So because the photon energy is deflected, and for pair production, it is increased. Okay, from the drop at Compton scattering region, the LSC increase at pair production region due to the photon energy which absorb again. For the half value layer that defined as the material thickness required to stop 50% of the gamma rays, we can see that the HBL have the like a maximum or increase at 11 mole percent. It is also due to the decrease in density. For the MFP, mean free path, which characterize the average distance a gamma photon travel between two successive interactions, we can also observe the increase at 11 mole percent. Also, we determine it is due to the decrease in density. For the electron total stopping power, we have also two regions. For the low energy region, You can see it is start to slow down, okay, because actually we have the collision loss. But suddenly at high energy it start to increase. It is due to the Bremsstrahlung radiation. For the electron stopping power, whenever we increase the bismuth, you can see it decreases linearly. Okay, it is due to the uh, bismuth element that is increased whenever we increase the bismuth element in the glass network, that is increased whenever we add the concentration of bismuth oxide. Okay, and then the loss value will be 15 mole percent. Also for the continuous slowing down approximation, you can see it is increased, okay, with the increasing bismuth concentration. Also it is increased with the increasing kinetic energy. It is due to the small mass of electron. So for the elastic properties, we can see that the average cross-link density, okay, it show a drop at 5 mole percent. It is due to the high formation of NBO. We know whenever we add the modifier, it will cause high formation of NBO. But at the Poisson's ratio, it observed a minimum at 7 mole percent due to the mixed ionic electron effect that caused by the blocking effect of this method. And last, elastic moduli, you can see the bulk modulus and shear modulus. We have a maximum at 7 mole percent made due to the blocking effect, which favor the formation of BO, which have the higher F. F is the average force constant. Hence, enhance the rigidity and bonding of the glass network at 7 mole percent. Thank you.